Hello, my name is Ozan Cem Baş. I'm a second year physics student in Bilkent. Today I will be presenting you my modern physics project, a measure which is the measuring of spin echoes using Earth field nuclear magnetic resonance. Quantum mechanical spin is an intrinsic property of particles. And ever since this property was discovered, scientists has found various methods to make use of this property. Nuclear magnetic resonance is one of these applications of this quantum mechanical property spin. And ever since it was discovered in 1940s, it has been one of the most important tools for chemistry and medicine and biology. The main intuition behind nuclear magnetic resonance can be explained like this. When you apply an external magnetic field to a particle that has this spin property, this particle behaves like a magnet because of this spin property and aligns with this external magnetic field. And after the particle is aligned with this external magnetic field, if you apply a signal at a frequency called Larner frequency that is perpendicular to this external magnetic field, it excites this particle, and the total magnetization of this particle follows a circular motion, and this causes this particle to emit, emit electromagnetic waves. And this can be recorded using electrical devices. And this property is different, and this behavior is different for different particles and different materials. Thus, this enables scientists to differentiate materials and measures different properties of materials using this spin property and the external magnetic field. And today, nuclear magnetic resonance has found a lot of applications in various areas of science and uh, medicine. However, it has its own drawbacks. This measured spin echo is a particularly weak signal, and to make it strong enough to be measured, you need either really precise measurement tools or you need a really strong external magnetic field. In hospitals or in chemistry laboratories, this external field is generated by permanent magnets or superconducting magnets, and is usually around the scale of Teslas, which is enormous. And uh, these permanent magnets are really delicate instruments, and they are really expensive to maintain as well. Also, due to their size and carriage limitations, they cannot be employed everywhere, and they need really specific conditions to operate. This makes application of nuclear magnetic resonance sort of limited. However, there are alternative methods in taking nuclear magnetic resonances, or NMR for short, called low field NMRs. This subfield of nuclear magnetic resonance includes using really low external magnetic fields to take NMR measurements. These low field NMR measurements tend to be usually much more cheaper than these high field NR measurements, like the MRI that is done in hospitals, due to the fact that obtaining these low magnetic fields is a lot easier and a lot cheaper. In our project, we wanted to demonstrate one of these low field NMRs called Earth field nuclear magnetic resonance, which is, as the name implies, making use of Earth's own magnetic field to take NMR measurements. In order to do this, we first had to build an experimental setup, which consists of two coils and a circuitry that gives the radio frequency to the sample of ours, and then reads off the spin echoes that occurs in the response. After building of this setup was completed, the only thing that was left to do was to connect these circuits to the correct power terminals and give the excitation signal with a signal generator to our sample inside this inside these coils that we use for excitation, and then we take measurements in out of from the output of the circuit. After doing the necessary calculations, we found out that the resonant frequency of water in the current magnetic field in our current location is around 2043 Hz. This is ideally the frequency that we are trying to see when we are taking a spin echo experiment. And here are the results that we have found. These are the figures of the measurements that were taken from the output of the circuit with and without the sample. In order to make sense out of these measurements, we first have to process them through taking Fourier transform of them. These are the Fourier transforms of the measurements that we have taken with and without the samples. As you can see, in both of them, we can see the peaks at 2043 Hz, which is not really ideal because we only want to see it in the one with the sample and don't want to see it in the one that doesn't have the sample. However, we can see that this peak is apparent even in the difference of these spectrums. In conclusion, we didn't quite achieve the quality of measurement that we were hoping to get. However, through the making process of these experiments and building these setups, we learned a lot about quantum mechanics and the spin property and taking NMR measurements. Thank you for watching.